December 7th, 1941. Pearl Harbor burns. The illusion of an ocean's worth of safety evaporates in a morning of fire and smoke. But as the last torpedoes find their mark and the battleships settle into the mud, a second silent catastrophe is already unfolding. Within 72 hours, the United States military faces a logistics nightmare. It has nothing to do with battleships or aircraft carriers. It is a crisis more fundamental, a crisis of shelter. Across the Pacific theater, from the jungles of the Philippines to the desolate shores of Wake Island, American forces are sleeping in canvas tents, the standard issue shelter, and they are disintegrating. Under the relentless assault of tropical downpours, a canvas tent, expected to last for months, is rendered useless in less than 3 weeks. In Washington, the War Department's morning briefings turn grim. The news from the front isn't about bullets, it's about water. Field reports arrive describing entire supply depots flooded, ammunition, carefully shipped 8,000 miles, ruined, radios, vital for communication, corroded into silence. Worse, they read reports of soldiers hospitalized with pneumonia because their shelter, their only refuge from the monsoons, literally fell apart while they slept. The very environment is defeating the army before the enemy even gets a chance. This is the first brutal lesson of the Pacific War. You cannot fight a global conflict if you cannot keep your soldiers dry. The obvious solution is the traditional one, wooden barracks, build solid structures. But the Pacific is not Pennsylvania. Traditional wooden barracks require 2 things the military does not have: skilled carpenters and time. They require lumber, which simply does not exist on remote coral atolls. To ship wood is to sacrifice space that could be used for bullets or food. The Navy's calculations are horrifying. To build conventional, long-term housing for the forces they need to deploy immediately, it would take 18 months. 18 months. In the chaos of early 1942, 18 months is an eternity. It is a lifetime. It is a guaranteed defeat. Before Brigadier General Eugene Raybould, the Army's chief of engineers, lies a problem not of strategy, but of physics. His engineers present him with what they call the impossible equation. The equation is simple. The military needs shelter. They need it for 50,000 men yesterday, and they will eventually need it for a staggering 2 million personnel scattered across hundreds of islands, bases, and continents. The requirements sound like science fiction. The structure must be manufactured in a factory in Pennsylvania, then transported 10,000 miles through submarine-infested waters. It must be lightweight, less than a Jeep, and the components must pack so efficiently they can fit onto a single railroad car. It must be assembled not by skilled carpenters, but by exhausted Marines, men who have perhaps never held a wrench, and they must be able to do it in a single day. Crucially, it must require no foundation, no concrete to pour, no complex site preparation. And then it must survive. It must survive 130-degree equatorial heat. It must survive Category 5 typhoons. It must survive monsoons that dump 15 inches of rain in 6 hours. And it must survive the very real possibility of Japanese bombing runs. Oh, and it must cost less than $1,000, and they need 10,000 of them ready to ship in 6 months. The impossible equation. Every existing solution is thrown at it. Every single one fails. Let's look at the options on the table in 1942. Option 1, the standard Army tent. The cost is perfect, $12, but as the field reports prove, it lasts 1 month if that. In jungle conditions, it is a mosquito-ridden, waterlogged death trap. It fails the resilience test. Option 2, the wooden barracks. This is the gold standard. It's comfortable, it's durable, but it costs $8,000 and requires a full construction crew for 6 weeks. It fails the logistics, assembly, and cost tests. But there is a third option, a clue from an ally, the British. They have been fighting longer, and their experience in North Africa offers a potential solution. Since 1916, they have used Nissen huts, semicircular steel shelters invented by Canadian engineer Peter Nissen during World War I. These corrugated iron half-cylinders can house 30 soldiers, require no specialized skilled labor to erect, and, in the words of one report, laugh at sandstorms. This is it. This must be the answer. But the Nissen design has critical, fatal flaws for a Pacific deployment. The Navy's engineers analyze the British blueprints and find 3 problems that doom the design. First, weight. The British version is heavy. Its panels require specialized lifting equipment to position. This is fine in a prepared European base, but impossible on a hostile beachhead. It fails the assembly test. Second, ventilation. The system is designed for the dry Libyan desert. In the 98-degree, 99% humidity of the Philippines, those same ventilation shafts turn the interior into a steel steam cooker, a sauna, unfit for human habitation. It fails the resilience test for the tropics. And most damaging, the Quonset Hut still requires custom foundation work. It needs concrete pads or carefully built wooden platforms to sit on, which brings you right back to the carpenter problem. It fails the assembly and logistics test. It is a brilliant solution for the wrong war. The equation remains unsolved. The math is brutal. At conventional construction rates, the war would be over, lost, before half the troops even had roofs. Soldiers are already writing letters home, letters describing how they wake up with their boots full of rainwater, how fungus grows on their uniforms overnight, how their temporary tents collapse during storms, sending men scrambling in the mud at 3 a.m. The medical corps reports are even more terrifying. In some sectors, respiratory infections, pneumonia, bronchitis, are hospitalizing more men than enemy action. This isn't just about comfort, it's about maintaining a fighting force, a force that doesn't rot away from the inside before it even sees combat. The call goes out. The specifications, that science fiction list, are sent to American engineering firms, to university research departments, and to the Navy's own fledgling construction battalions. The message is clear. Solve this. Solve it now. It's February 1942. The war is being lost. The problem seems impossible. And somewhere, in a cold warehouse in Quonset Point, Rhode Island, a small team of engineers is about to turn architectural impossibility into reality. February 1942. The crisis is set. The equation is written. In a peculiar twist of wartime cooperation, the first piece of the puzzle arrives at the Navy's Bureau of Yards and Docks. It comes from the British. Grateful for American supply shipments, British engineers share the detailed technical drawings for their best solution, the Quonset Hut. On paper, it's the answer. 16-foot wide semicircular tunnels made from corrugated iron sheets bolted to a wooden frame. Commander John Philip Drosfeld studies the specifications. He immediately sees both its genius and its catastrophic problems. The genius, the arch shape. Just like the British discovered in World War I, the arch naturally deflects wind and sheds water without complex engineering. It's strong and simple. But then Drosfeld's red ink comes out. The problems. A laundry list that would doom the design in the Pacific. First, the British huts weigh 3 tons when disassembled. They require foundation bolts drilled into concrete. This fails the no foundation and lightweight test. Second, the frame. The iron sheets are bolted to an internal wooden frame. Drosfeld knows what happens to wood in the tropics. It becomes a feast for termites. A single colony of carpenter ants can reduce a support beam to a hollow shell in 1 season. He circles the ventilation specs. 2 small windows, designed for the cool, damp weather of Scotland, would turn these steel tunnels into ovens at Guadalcanal's 98-degree average temperature. It was a pressure cooker, not a shelter. The Quonset Hut wasn't the solution. It was just a better articulation of the problem. But there is another American voice in this conversation, an influence that comes from an unexpected corner. He is an architect, a philosopher, an inventor. And in 1942, most of the world dismisses him as a crank. His name is Buckminster Fuller. Since the 1920s, Fuller had been preaching the gospel of prefabricated housing. His Dymaxion house concept, factory-built, lightweight, assembled on site, made of industrial materials, it reads like prophecy. In 1942, Fuller's ideas about mass-producing housing like automobiles, using steel and aluminum instead of traditional lumber, designing for rapid deployment, suddenly, these ideas sound less crazy. The military hasn't directly consulted Fuller. They don't need to. His published papers are circulating through every engineering department in the country. And his core insight proves invaluable. Treat buildings like manufactured products, not construction projects. The Navy consolidates this new thinking at a freshly commissioned air station on Narragansett Bay, Quonset Point, Rhode Island. The location isn't random. Rhode Island has deep manufacturing expertise in sheet metal, born from its jewelry and silverware industries. It has proximity to the steel mills of Pennsylvania and to shipyards that understand intimately what marine-grade corrosion resistance really means. In March 1942, the Navy assembles an unusual team. It's not just Navy brass. They bring in structural engineers from the Strand Steel Corporation, men who had spent their lives building prefabricated farm buildings. They bring in architects from the George A. Fuller Construction Company, men who specialize in rapid assembly methods. And crucially, they add Navy officers who have actually served in the Pacific. Men who know what typhoon-proof really means versus what it means on paper. The team lead, Otto Brandenberger, brings that farm building experience from Strand Steel. And it turns out, building a barn for the Midwest is exactly the right experience for this problem. His Strand Steel barns used a simple, elegant trick, self-supporting arched panels. This was Brandenberger's radical proposal. Look at the Quonset Hut. It's a wooden skeleton with a steel skin draped over it. Brandenberger proposed they eliminate the wooden skeleton entirely. No wood for termites to eat. No complex joinery to fail during storms. He proposed they make the corrugated steel skin, the skin itself, carry all the loads. This violates conventional architectural wisdom in 1942. In 1942, steel is for bridges and skyscrapers held together by massive internal frames. It is not supposed to be the building. But Brandenberger knows something they don't. He knows his simple farm barns have survived Midwest tornadoes without any internal framing, and he is willing to bet the same principle can be scaled up for war. The British contribute another crucial element through their painful experience. Their Quonset huts in Burma and Singapore have taught them exactly how tropical environments destroy buildings. The reports read like horror stories. Fungus isn't just cosmetic, it literally eats through wood preservatives. Humidity doesn't just make things damp, it corrodes metal fasteners until roofs collapse. Carpenter ants aren't just annoying, they reduce support beams to dust. But these horror stories provide the Quonset team with a checklist of everything that must be engineered out of the design from day one. No wood in contact with the ground. All steel must be hot-dip galvanized, not just painted. Ventilation must be aggressive enough to prevent condensation. Every fastener must be accessible for replacement without disassembling the structure. By April 1942, the hybrid vision crystallizes. Take the Quonset hut's brilliant arch geometry. Strip out everything that makes it heavy, vulnerable, or slow. Add Buckminster Fuller's mass production philosophy. Add Brandenberger's frameless steel barn design. And then engineer every last detail for the specific, unrelenting hell of Pacific Island warfare. April 15, 1942. Otto Brandenberger walks into a Quonset Point warehouse with 30 engineers and a deadline. A deadline that would be laughable if the war situation weren't so desperate. 60 days. 60 days to design, prototype, test, and approve a completely new building system that does not yet exist. The team works in shifts around the clock. They sleep on cots pushed against the warehouse walls. They subsist on Navy mess hall coffee and the kind of intense, suffocating pressure that either produces brilliance or complete collapse. Brandenberger divides his crew. One team tackles aerodynamics. Another figures out how to nest components for shipping. A third works exclusively on the joint and fastener problem that plagued the British design. The first radical decision happens on day 3. Traditional architectural drawings take weeks to produce. The team doesn't have weeks, so they don't draw the building. They build it in real time. They sketch a detail in the morning, have the metalworking shop fabricate it by afternoon, test it to failure overnight, and revise the design by dawn. This iterative prototyping approach is standard practice in Silicon Valley today. In 1942, it is revolutionary. The warehouse floor becomes a laboratory, scattered with failed joints, bent test panels, and increasingly refined versions of each component. They steal a technique from aircraft manufacturing. Every part gets a number, every revision gets documented, and nothing moves to the next prototype generation without solving the previous version's failure points. The revolutionary process of real-time prototyping wasn't just chaos. It was a pressure cooker forcing rapid evolution. The first problems to be solved weren't elegant engineering, but brutal practicality. The dimensions, for instance, were not born from aesthetic choice. They were dictated by the American railroad system. The final hut had to be 16 feet wide. Why? Because that was the absolute maximum that could fit on a standard rail car without requiring special permits. The sections were 20 feet long. Why? Because that was short enough for a four-man crew to lift a panel, but long enough to create usable space. The standard final length, 48 feet. Capacity, 36 men with bunks. The Quonset team discovered this size hit a perfect sweet spot in structural engineering. Make it smaller and you waste precious shipping capacity. Make it larger and the panels become too heavy for field assembly, or the arch starts requiring internal supports, reintroducing all the problems they were trying to eliminate. But the single most critical calculation, the one that consumed 2 full weeks of their priceless 60-day deadline, was the arch radius. Too flat, and the wind forces in a typhoon could peel the structure open like a sardine can. Too steep, and you waste interior headroom and create impossibly complex geometry for the end walls. After hundreds of calculations, Brandenburger's team settled on an 8-foot radius, a perfect semicircle. This was the masterstroke. This shape provided 7 feet of headroom at the sides, and it created what structural engineers call a self-bracing arch. The corrugated steel naturally wants to hold this curve. This meant the panels could be thinner, and therefore lighter, than flat sheets would require for the same strength. They ran the load calculations. The design could, in theory, handle snow loads up to 40 pounds per square foot and wind speeds exceeding 100 miles per hour. But theoretical calculations and Pacific typhoons are two very different animals. By day 40, they have something that looks like it might work. A Frankenstein's monster of riveted panels, experimental joints, and borrowed hardware. The first complete prototype goes up on May 25, 1942. It's assembled by 6 sailors who've been given 4 hours of instruction and basic hand tools. The final assembly time, 14 hours. 14 hours. It's encouraging, but it's not good enough. The Navy wants single-day construction capability. A day on a combat beachhead isn't 14 hours. It's the 8 hours of daylight you have before the bombers return. Marine landing schedules do not allow for multi-day building projects. The prototype is a failure. The team identifies the bottleneck immediately. It's not the walls, it's not the roof, it's the floor system. They had been trying to include a wooden floor as part of the package, assuming soldiers needed to be off the ground. But this wooden floor was complex, slow to assemble, and, as the British reports had warned, the very first thing to rot in tropical conditions. The solution is elegant in its brutal simplicity. Eliminate the floor. Eliminate it entirely from the basic design. The hut will sit directly on whatever surface exists, coral, sand, dirt, or gravel. If a unit required a finished floor for a medical station, that could be added later as a separate project. But the basic shelter achieves weather protection without it. This single decision cuts assembly time from 14 hours to a blistering 8 hours. It shaves 1,200 pounds off the shipping weight. It solves the problem. On June 10, 1942, exactly 58 days after starting, the final prototype stands complete. 96 corrugated steel panels, each weighing less than 50 pounds, bolted together to create 720 square feet of enclosed space. Total materials cost $1,394. Total weight, 9,000 pounds. The 60-day miracle is complete. The engineers have solved the impossible equation, but the celebration is short-lived because the real test begins, the engineering equivalent of an interrogation. Navy structural engineers arrive from Washington. They carry wind load tables, meteorological data from the Pacific, and a healthy, profound skepticism that this corrugated steel tunnel can survive what nature actually throws at tropical islands. The numbers they're working with aren't theoretical. They are pulled from actual terrifying weather events. Typhoon Gloria, which hit Guam in 1940 with sustained winds of 140 miles per hour. The 1935 Labor Day hurricane, which drove wooden planks through palm trees like spears. If a Quonset hut fails in a storm, the result isn't just property damage, it's dead servicemen. Brandenburger's team starts with the fundamental physics. First, aerodynamics. When wind hits a flat wall, it pushes with maximum force. but a curved surface deflects the wind, splitting the force, sliding it up and around. Think of how water flows around a smooth river stone versus slamming into a dam wall. The profile means hurricane force winds slide over the structure rather than trying to punch through it. Second, the corrugations. Those ridges add a second layer of brilliance. They create structural rigidity, the same way folding a piece of paper makes it strong enough to support weight. Each corrugation acts like a tiny I-beam, resisting bending forces. And finally, the most important principle, the compression ring. In a conventional building, the roof pushes down on the walls. Storm winds can literally lift the roof off. The Quonset arch is a single, continuous curve. Every panel shares the load with its neighbors. It's the same principle that keeps ancient Roman stone bridges standing for centuries. The structure works with physics, not against it. The theories are impressive, but they mean nothing without proof. So the Navy sets up validation experiments that border on sadistic. Test 1, the nor'easter. They build a full-scale hut at Davisville and instrument it with strain gauges and pressure sensors. Then they wait. On March 3, 1943, a vicious storm hits with 75-mile-per-hour winds and heavy, wet snow. Perfect. The instruments record the structure flexing by less than 2 inches at its crown, then returning to its original shape when the wind subsides. The joints hold. Nothing leaks. The structure behaves exactly as the calculations predicted. But the tropical environment test proves more challenging. You cannot simulate years of jungle rot in a Rhode Island warehouse. So, the Navy ships a test unit to the Panama Canal Zone. Humidity, 85% year-round. Temperature, always above 80. 6 months later, the report comes back. The news is good. Minimal corrosion on the galvanized panels, no structural degradation. But there is one serious, unexpected problem: interior condensation. When the hot, humid daytime air hits the relatively cooler steel at night, water literally rains from the ceiling inside the hut. The design is too weatherproof. The solution? Add ventilation louvers at both ends and along the ridgeline. Openings to let hot air escape and create airflow. These vents add $47 to the unit cost, but they transform the hut from a steel sauna into something humans can actually occupy. The iterative design process works. The final engineering challenge is the foundation. How do you anchor it without concrete? The answer comes from tent technology, scaled up. Massive steel stakes, driven into the ground, connected to the hut's base with adjustable tension cables. The system is brutally simple. June 1942. The War Production Board approves the Quonset Hut for mass manufacturing. The 60-day miracle is over. The interrogation is complete, the design is locked, and what happens next is American industrial capacity, waking from its slumber and operating at its absolute peak. June 1942. The War Production Board gives the green light. The 60-day miracle is over. The real war effort begins. What happens next is American industrial capacity, a sleeping giant awakened by Pearl Harbor, operating at its absolute terrifying peak. The Navy doesn't just contract with one company. It contracts with 10 major steel fabricators across the Midwest and Northeast. Companies that were making grain silos and water tanks 6 months ago are now retooling their entire existence for military shelter production. The Strand Steel Corporation converts its entire Philadelphia facility. George A. Fuller Construction takes over a former automobile parts plant in Chicago. Great Lakes Steel dedicates 2 entire rolling mills to nothing but corrugated panel production. By August, just weeks after approval, these factories are collectively producing 1,500 complete huts per week, and the number keeps climbing. The manufacturing process is not construction, it's pure automotive assembly line logic. Massive steel coils arrive by rail. Rolling machines corrugate the flat steel, a process that work hardens it, making it even stronger. But the most crucial step is not the shaping, it's the protection. It's a process that would define the Quonset Hut's future. Hot dip galvanizing. The panels are dipped in molten zinc at 850 degrees Fahrenheit. This isn't paint, it's a metallurgical bond. The zinc coating chemically sacrifices itself to corrosion before the underlying steel can rust. In the salt spray air of the Pacific, this single step, this $112 extra cost, means the difference between a 5-year lifespan and a 50-year lifespan. It was proven non-negotiable. And then, the logistical masterpiece. Each complete hut kit, every panel, every end wall, every single nut and bolt, is packaged with obsessive attention to shipping. The plywood end walls are packed flat. All hardware is boxed in a single crate, which includes illustrated assembly instructions, designed for men who might not even read English. But the true genius was in the steel. The 96 corrugated panels nest inside each other like stacked bowls. A stack of 96 separate panels would be over 8 feet tall. A nested stack of 96 Quonset panels is just 14 inches tall. This packaging density is a strategic weapon. The entire hut loads onto one standard 40-foot flatbed railcar. There is zero wasted space. The shipping choreography is wild. Trains leave Philadelphia and Chicago daily, racing to ports in San Francisco and Seattle. A single Liberty ship can carry 200 Quonset huts. That is shelter for 7,200 men. The War Shipping Administration tracks every manifest. These aren't just buildings. They are strategic assets, as vital as tanks or ammunition. But the design's true genius only shines on the receiving end. This is where the Navy's new construction battalions, the famous Seabees, turn engineering into reality. They develop standardized procedures that turn shelter erection into a choreographed operation. 6-man crew, 8 hours, 1 complete hut, level the ground. 2 men handle the end walls while 4 wrestle the 50-pound steel panels. They overlap by 6 inches. They bolt together. No welding, no concrete, no skilled carpentry, just wrenches, a level, and illustrated instructions. The speed record is set on Espiritu Santo in 1943, when a specially trained crew erects a complete hut in 4 hours and 17 minutes. But that's just showboating. The real achievement is sustained production. Crews throwing up 5 or 6 huts per day after day, building entire bases faster than the Japanese can bomb them back to rubble. By December 1943, monthly production hits 8,000 units. The cost accounting tells the victory story. 1 conventional barracks, $12,000, 400 man-hours of skilled labor, 6 weeks of construction time. 1 Quonset hut, $1,394, 60 man-hours of unskilled labor, 8 hours of construction time. The Quonset delivers shelter at 1/10 the cost in 1/20th the time. By mid-1944, over 160,000 units are deployed, housing for nearly 6 million personnel, built in less than 2 years. The impossible equation was solved in the lab. But the lab tests at Quonset Point were one thing. The battlefield is another. Trial by fire, Guadalcanal, August 1942. The first combat-deployed huts arrive on a beach where the temperature is 95 degrees with 90% humidity, and Japanese bombers make daily visits. Marine engineers unload the flat-packed panels under sporadic artillery fire. Within 12 hours, Henderson Field has 10 new structures housing maintenance crews. The real test comes 3 days later. A Japanese bombing run scores a near miss. A 500-pound bomb detonates 40 yards from a hut full of aviation mechanics. The blast wave flattens palm trees. It shreds canvas tents like tissue paper. But the Quonset flexes. Dirt and shrapnel rattle off the corrugated steel, and when the smoke clears, the structure stands intact. Every man inside shaken but alive. But the jungle proves as hostile as the enemy. Within 2 weeks, rust appears on ungalvanized fasteners. Fungus grows on every surface. The ventilation louvers that seemed adequate in Rhode Island are useless here. Marines start cutting their own holes with tin snips. These modifications are documented and sent back to Quonset Point. The iterative design process continues from the battlefield. Trial by ice, the Aleutian Islands, Alaska. Here, the design faces the opposite hell. Temperatures plunge to -40. Winds exceed 100 miles per hour. The cold makes the standard steel brittle. Early units suffer from panels cracking at the bolt holes. Engineers at home respond. They specify a new cold-rolled steel with different metallurgy for Arctic deployments. They add rubber gaskets at every joint. The weatherized Quonset is born. Trial by steel, Palermo, Sicily. A Quonset hut, pressed into service as an ammunition depot, takes a direct hit from a German 88mm artillery shell. The shell penetrates the steel skin. It detonates inside, among crates of ammunition. The resulting explosion should have vaporized the structure. Instead, the arch shape, that compression ring the engineers designed in Chapter 3, channels the blast force outward. It blows the walls and roof panels off, but the structural frame, though twisted, is left standing. EOD crews note that a rectangular building would have collapsed completely, burying everyone. The arch's inherent strength means even catastrophic damage doesn't trigger total structural failure. But the ultimate stress test comes in December 1944. Super Typhoon Cobra hits the Philippines. Winds are measured at 140 miles per hour. At Tacloban, the storm destroys 80% of all structures on the base. Wooden buildings explode into splinters, concrete block structures collapse. But of the 43 Quonset huts on that base, 39 survive intact. The 4 that fail, engineers find they were improperly anchored. The design itself was proven. By war's end, field performance data from 50 combat zones has fed back into the design. The 1945 production model is a battle-hardened, perfected piece of engineering, worlds apart from the 1942 prototype. May 8, 1945. Victory in Europe. August 15, 1945. Victory over Japan. The world celebrates. And suddenly, the United States military owns roughly 170,000 Quonset huts scattered across 6 continents and has absolutely no idea what to do with them. May 1945. August 1945. Victory. The world, shattered and exhausted, begins to rebuild. And the United States military, the greatest industrial power on Earth, now owns roughly 170,000 Quonset huts scattered across 6 continents. The original plan assumed these were temporary wartime expedients, disposable tools that would be scrapped or abandoned once permanent facilities could be built. But something unexpected happens. Nobody wants to get rid of them. At the same time, a new crisis is brewing at home. Veterans return by the millions, victorious, ready to start their lives. And they discover a housing shortage so severe that families are living in converted chicken coops, sharing apartments with 3 other families. The construction industry, starved of materials and labor during 4 years of total war, simply cannot build fast enough. The War Assets Administration, tasked with liquidating surplus military property, finds itself facing an unusual problem. There is more demand for used Quonset huts than they have inventory to sell. Into this domestic crisis, the Quonset hut steps in, ready to fight a new kind of war. It's offered to veterans at liquidation prices, $1,000 to $2,500 for a complete structure that would cost $8,000 to build conventionally. If you could even find someone to build it. And so the Great Migration begins. By late 1946, entire suburban developments made of Quonset huts spring up. Roger Young Village in Los Angeles houses 750 families. Vetvilles appear near universities, flooded by students on the GI Bill who need immediate housing. And a fascinating architectural adaptation starts. Families add wooden facades to the curved ends, making the structures look less like military surplus and more like quirky cottages. Interior walls divide the open space. Windows are cut into the steel sides, violating every structural principle, but making the spaces truly livable. The military shelter becomes a home. But housing is just the beginning. The baby boom is hitting. Suburban populations are exploding, and they need more than homes. They need communities. Churches discover the Quonset hut solves a different, impossible equation, providing worship space without the decade-long capital campaigns. First Presbyterian Church of Levittown, Pennsylvania, holds services in a Quonset hut for 15 years. Dozens of congregations make the same calculation. $2,500 for immediate space beats $150,000 for eventual grandeur. The acoustics are terrible. The aesthetics, underwhelming. But people can gather for worship next month instead of next decade. Education sees the same adoption. School districts face the same impossible math that plagued the military in 1942. They need classrooms now. By 1950, an estimated 3,000 schools across America include at least one Quonset classroom. Students spend their entire elementary education in these steel tunnels, learning multiplication tables under the same curved ceilings that once sheltered bomber crews in the Pacific. The commercial sector joins the party. Machine shops, auto garages, warehouses. The clear span space, no internal support columns, makes it perfect for industrial work. The Quonset hut becomes embedded in the American visual landscape. It becomes a symbol of practicality over pretense, function over form, the ingenuity of making do. Architectural historians initially dismissed them as temporary eyesores, but to understand why the Quonset hut is truly a brilliant design, you must look at modern disaster zones. When the 20,000 Haiti earthquake destroys Port-au-Prince, relief organizations face the exact same equation American military planners confronted in 1942. Immediate shelter for hundreds of thousands, no infrastructure, no time for conventional construction. And the solution that emerges is the Quonset hut's great-grandchild. The United Nations High Commissioner for Refugees now uses systems called RHUs, refugee housing units. They are essentially Quonset huts with 80 years of material science improvements. Instead of corrugated steel, insulated composite panels, instead of bolts, snap-fit connections. But the core concept is identical: curved profile for wind resistance, self-supporting arch, flat-pack shipping. A two-person crew can erect a modern RHU in 4 hours, almost exactly matching the 1942 specification. The physics haven't changed. After Hurricane Katrina devastated the Gulf Coast in 2005, engineers studying which buildings survived found, unsurprisingly, that curved structures consistently outperformed rectangular ones. Entire neighborhoods of conventional homes were reduced to foundation slabs, while a handful of Quonset-style metal buildings stood intact. This triggered a wave of research into what engineers now call aerodynamic architecture, designing buildings to work with wind rather than resist it. The result looks remarkably like a Quonset hut, because wind flowing over a curve today creates less pressure than wind slamming into a flat surface, exactly as it did in 1942. The military applications never stopped. The U.S. Armed Forces still deploy arch-style shelters, but now they are made of aluminum alloys reinforced with Kevlar. They deploy from shipping containers, unfolding like origami, and can survive IED blast waves. If you showed a 2025 deployable shelter to the 1942 Quonset Point team, they would immediately recognize their own design philosophy. The economic argument also remains unchanged. A modern engineered arch shelter costs about $50 per square foot. Conventional construction in that same remote location, $150 to $300 per square foot. The math that drove the Quonset development, how do you shelter the most people for the least money in the shortest time, hasn't changed. But perhaps the ultimate validation, the final proof of the Quonset hut's genius, comes not from our past, but from our future. On Mars. When NASA and private space companies design habitats for a Martian colony, what constraints do they face? An extreme hostile environment, no infrastructure, minimal tools, unskilled assembly by astronauts who are not carpenters, and the need for maximum strength from minimum materials that must be shipped not 10,000 miles, but 100 million miles. The constraints of interplanetary construction mirror the Pacific Theater of 1942 so precisely that engineers, 80 years later, independently rediscover the exact same solution. Proposed Martian shelters are not rectangles. They are prefabricated, self-supporting arches. When humans finally build permanent shelters on another planet, there is a reasonable chance those structures will owe their design heritage to 30 engineers working in a Rhode Island warehouse during the darkest days of World War II, solving an impossible problem with corrugated steel and brilliant simplicity. This story is more than just military engineering. It's a timeless testament to the power of innovation under pressure. It proves that the most severe constraints, no time, no materials, impossible requirements, and lives on the line, are not barriers. They are the most powerful catalysts for genius. Faced with an impossible equation, the engineers at Quonset Point didn't try to perfect the old. They redefined the problem entirely. The most inspiring lesson is that remove the floor moment, a brilliant stroke of pure pragmatism. They willingly sacrificed perfection for speed, proving that good enough fast enough is infinitely more valuable than perfect but too late. Their legacy isn't just 170,000 steel structures. It's a timeless philosophy. Simplicity is resilience. Adaptation is more important than the initial plan. And when faced with a problem that seems impossible, human ingenuity, fueled by absolute necessity, will always find a way.